Hello. So let's go ahead and do lecture 6 again because my previous video was inadequate. Okay, so in lecture 5 in previous lectures, we talked about this affine connection or linear connection, which is a map which has two inputs. First, a smooth vector field, and the second is a smooth section of a vector bundle. And the output is a smooth section of a vector bundle, okay? And essentially we're thinking of this as like we take a smooth section of a vector bundle, most often a tensor field, and we take the derivative in some direction, the direction x, which is the input smooth vector field, okay? And this operation is tensorial in the first argument, so it's C infinity m linear with respect to the vector field that we're taking the derivative in the direction of. And then it obeys the Leibniz rule in the second argument, okay, with respect to this tensor field, this smooth section of the vector bundle. So namely, if f is a C infinity function, function from m to, let's say, our field, which let's just say is the complex numbers, and S is a smooth section of the vector bundle. Let's say the vector bundle is E. Then we have the Leibniz rule, nabla x of fs is equal to f nabla x of s plus xf times s, okay? So the covariant derivative of fs in the direction x is equal to f times the covariant derivative of s in the direction x plus the covariant derivative of f in the direction x, which is just xf times s, okay? All right, so if we look at the tensor bundles, okay, so instead of just an arbitrary vector bundle, we're going to now look at the tensor bundles. So if we look at the trivial tensor bundle, this is a zero-dimensional, or not zero, yeah, it's basically, it's not zero-dimensional, but still infinite-dimensional, actually. But it's rank 0, 0 tensors, okay? What are those? Those are just smooth functions, okay? So our vector space that we're attaching to every point in the manifold is just the complex numbers. And so a smooth section of that vector bundle is just a smooth function, okay? So so the tensor 0, 0, so T00M is a set of 0, 0 tensors, is just the set of smooth functions, okay? If we look at this this vector bundle, okay, then there's an obvious choice for the covariant derivative or the affine connection, namely nabla xf is equal to xf, right? It turns out you can choose a different, there's a more general choice, which is you can take an arbitrary one form, omega, and then set nabla x of f equal to xf plus f omega of x, okay? And you can just check that satisfies the Leibniz rule, the linearity in the first argument, and so it is a linear connection on this line bundle, which is the T00M, okay? So I'll just show you the formula real quick. It's right there, okay? All right, so moving on, we now want to, given a linear connection on the tangent bundle, okay, which is T10 of m. So tangent bundle is T10 of m, first of all. So just to recall the notation, like TRSM is basically this is the set of tensor fields which take R inputs, which are covectors, and S inputs, which are vectors. Okay, and basically so the first R inputs are covectors, then the following S inputs are vector fields, and you have a multilinear map that factors through a tensor product. Okay, so it gives you a tensor field. So 1, 0, T10 M is we have one input that's a covector, 0 inputs that are vectors, so that's just a vector field, right? A vector field takes in a covector, spits out, the obvious evaluation of, x of omega is omega of x, basically, okay? All right, so we're given a linear connection on the tangent bundle, and we wish to construct we also have a linear connection on the line bundle, okay? And we're going to choose the trivial connection on the line bundle. So this is just, so again, the line bundle is the bundle M cross C, where C is the complex numbers. Okay, so M cross C, where C is the complex numbers. We're just attaching the complex numbers to every point of the manifold, and smooth sections of this line bundle are just smooth functions. And we're going to choose the canonical linear connection on this line bundle, which just means we're choosing, for any smooth function x, we're setting nabla x of f to be equal to xf. Okay, so together with those two choices, we're given a linear connection on the tangent bundle, and we're choosing the canonical linear connection on the line bundle. Okay, then we wish to construct a natural linear connection on the cotangent bundle with that information. Okay, so in order to do this, we need to use the conceptual guidance provided by the parallel transport structure. Okay, so recall that this linear connection, which is specified on the tangent bundle, will give rise to a parallel transport structure, okay, which is a family of linear isomorphisms. Basically, for any curve gamma, in the manifold, we have let's say gamma goes from 0 to t, then gamma is parametrized from 0 to t, then we have a isomorphism of the tangent spaces at gamma of 0 and gamma of t, okay? And so we're going to call that linear isomorphism P0t. So P0t is the, P superscript gamma subscript 0t is going to be the parallel transport map, which is induced by the linear connection between the tangent space at gamma of 0 to the tangent space at gamma of t, okay? Now, we can use this every isomorphism of these tangent spaces gives rise to an isomorphism of the dual spaces, okay? But it's in a way that we take. Okay, I'm going to continue this in the next video.